there was a time before the Earth existed at all. No oceans, no mountains, no sky to speak of, and no ground beneath any sky. Just a vast, cold cloud of gas and dust drifting quietly through a dark and empty region of space more than 4.5 billion years ago. This is the story of how that cloud slowly became a planet, how it cooled and cracked and filled with water, how, against almost impossible odds, it grew warm oceans and gentle forests and, eventually, minds capable of wondering how it all began. We will follow the Earth from that first formless cloud all the way to the world we know today, and beyond it, into the distant future that still awaits. It begins, as so much in the universe does, with gravity, patience, and a very long stretch of time. Somewhere within that ancient cloud, a slow rotation had already begun. Very gradually, gravity started pulling the gas and dust inward. And as it did, the whole cloud began to spin a little faster, the way a skater spins faster when she draws her arms in close. Some scientists think this collapse may have been triggered by the shockwave of a nearby exploding star, a supernova, sending a gentle push through the cloud and setting the long process in motion. Whatever the trigger, the cloud began to fall in on itself and everything that followed. The sun, the planets, the earth beneath our feet grew out of that single collapsing cloud. Most of the material gathered at the center. As more and more gas piled inward, the pressure and heat at the middle of the cloud climbed higher and higher until finally conditions became extreme enough to ignite nuclear fusion. A star switched on. That star was the sun. Not all of the cloud fell into the new star, though. Because the whole system was spinning, the leftover material couldn't simply collapse straight inward. It flattened instead into a wide spinning disk that circled the young sun, a little like the rings of Saturn, but far larger, and made of gas, dust, and rubble rather than ice. Astronomers call this the protoplanetary disk. It was inside this slowly turning disk, over the course of several million years, that the planets began to take shape. The Earth was one of them. The disk itself was not the same all the way through. Near the young sun, temperatures were fierce enough to keep most materials in a hot, vaporous state, allowing only rock and metal to condense into solid grains. Farther out, beyond a boundary sometimes called the frost line, temperatures dropped low enough for ice to form as well, and the raw material available for planet building became far more abundant. This single difference in temperature, more than almost anything else, explains why the inner solar system ended up with small, dense, rocky worlds like the Earth, while the outer solar system grew giant planets built largely from gas and ice. We happen to form on the warm, rocky side of that boundary. But first, nothing about this process looked much like planet building. It looked more like dust settling. Tiny grains, no larger than specks of ash, drifted through the disk and occasionally brushed against one another. Some of them stuck together, held by nothing more than weak static forces, the same kind of stickiness that makes dust cling to a wool sweater. Slowly, these tiny clumps grew into something like pebbles. The pebbles collided and stuck to become boulders. The boulders, over time, became small worlds in their own right, bodies a few kilometers across, known as planetesimals. Once a planetesimal reached a certain size, something changed. It became massive enough to have a meaningful gravitational pull of its own, and from that point on, it no longer had to wait for chance collisions. It could actively draw in nearby material, growing faster and faster as it swept up dust, pebbles, and smaller bodies from an ever-widening region of the disk around it. Astronomers sometimes call this stage runaway growth, because the largest bodies pull ahead of their smaller neighbors at an accelerating pace. The way a snowball rolling downhill gathers snow faster, the bigger it gets. Closer to the young sun, where temperatures were too high for ice to survive, the planetesimals formed almost entirely from rock and metal. It was out of a great many of these rocky bodies, colliding and merging again and again over tens of millions of years, that the Earth slowly assembled itself, alongside its rocky neighbors, Mercury, Venus, and Mars. Every collision released heat, and there were countless collisions. By the time something resembling a young Earth had come together, a large part of it was molten or close to it. A glowing, restless ball of rock rather than the solid blue-green planet we know today. Scientists sometimes refer to this stage as a magma ocean, not water, but liquid rock, covering the young planet from one horizon to the other, deep enough in places to reach hundreds of kilometers down toward the core. That early molten state mattered more than it might seem. Inside a body that is largely liquid rock, heavier materials sink and lighter materials rise, the same way oil separates from water if you leave the two sitting together. Iron and nickel, being dense, sank down toward the Earth's center. Lighter silicate rock rose toward the surface. Scientists call this process differentiation, and it's the reason the Earth today has the layered structure it does. A dense metallic core at the center, a thick rocky mantle around it, and a thin outer crust on top, the part we actually stand on. We know, from careful measurements of certain isotopes locked inside ancient rocks, roughly how quickly this sorting happened. Elements like hafnium and tungsten decay and transform into one another at very precise, known rates, and by comparing how much of each is found in different types of rock today, scientists can work backward to estimate when the Earth's core finally separated from its mantle. The evidence suggests this happened astonishingly early, within perhaps the first 30 to 50 million years of the planet's existence, a geological instant compared to the 4.5 billion years that would follow. The heat released by this sinking and settling, combined with heat from the slow decay of radioactive elements trapped inside the young planet, kept the Earth's interior hot for a very long time. In a modified form, that heat is still driving geological activity deep underground today, still slowly leaking outward after more than 4 billion years. Before the Earth had even finished forming, something happened that would shape nearly everything that came afterward. Sometime within the first 100 million years or so of the solar system's history, while the inner planets were still coming together, the young Earth appears to have collided with another planet-sized body, one roughly the size of present-day Mars. Scientists sometimes give this vanished world an informal name, Theia, after a titan from Greek mythology said to be the mother of the moon. This was not the only idea scientists once considered for how the moon might have formed. Earlier in the 20th century, some researchers proposed that the moon might have split away from a rapidly spinning young Earth, flung outward by centrifugal force like water flicked from a spinning wheel. Others suggested the moon might have formed somewhere else entirely in the solar system and simply been captured later by Earth's gravity as it passed close by. Both ideas have largely fallen out of favor, unable to account for the detailed chemistry of moon rocks as convincingly as the giant impact idea does. Science rarely settles on an explanation quickly or by guesswork alone. It tends to arrive there slowly, by testing many possibilities against the evidence and letting the weaker ones fall away. The collision with Theia, if it happened as currently understood, was immense. Much of both worlds is thought to have melted or vaporized on impact, and a huge amount of that vaporized material didn't simply fall back to Earth or drift away into space. Instead, it settled into orbit around the battered young planet. Over what was likely a matter of centuries rather than millions of years, this glowing ring of debris cooled and gathered itself together, forming the moon. Picture that moment if you can. A sky lit not by a calm, pale disk, but by a churning ring of molten rock and dust, glowing faintly orange and red, wrapped around a scarred and steaming young Earth. Within what was, by geological standards, no time at all, that ring pulled itself into a single sphere, and the Earth had a companion. This idea, the giant impact hypothesis, fits the evidence surprisingly well. Rock samples brought back from the moon by astronauts in the 20th century turned out to closely match the chemistry of the Earth's own mantle. And the moon has an unusually small metallic core for its size, exactly what you'd expect if it formed mostly from the outer, rocky layers of two colliding worlds, rather than from their dense metal centers. The moon that resulted from this violent beginning would go on to become one of Earth's quiet, steady companions. Its gravity helps stabilize the tilt of Earth's axis, keeping our seasons far more regular than they might otherwise be over millions of years, rather than swinging wildly and unpredictably the way Mars's axis, lacking a large moon of its own, is thought to have done throughout its history. Later, once oceans existed to feel its pull, the moon would also give the Earth its tides. A slow, rhythmic rise and fall of the sea that some researchers think may even have helped early life make its first tentative moves from water onto land. A story we'll return to later. In its earliest days, the moon also sat much closer to the Earth than it does now. Perhaps only a tenth of the distance separating the two worlds today. From the surface of the young Earth, had anyone been there to see it, the moon would have filled a startling portion of the sky, far larger and brighter than the familiar disk we see tonight. Over billions of years since, the moon has been slowly, quietly drifting away from us at a pace of a few centimeters each year, gradually easing itself outward into the more distant orbit it holds today. That closeness came with another consequence, one easy to overlook. The young Earth also spun much faster on its axis than it does now. A day, in these earliest times, may have lasted only 5 or 6 hours, rather than the 24 we take for granted, with the sun racing across a vast, blurred sky, rising and setting again before what would today feel like a single ordinary afternoon had passed. The moon's gravity, tugging gently on Earth's oceans and even on its solid body, has spent the whole of the time since gradually slowing that spin down, stealing a little of Earth's rotational energy with each pass and carrying it off as it drifted farther away. The lengthening has been so gradual, so evenly spread across billions of years, that no single generation of anything living could ever have noticed it happening. Only by comparing the fine growth lines in certain ancient fossil corals and shells, which record daily and yearly growth much like tree rings, have scientists been able to confirm that days on Earth truly were shorter, hundreds of millions of years ago, than they are now. For now, though, the Earth was still a long way from anything resembling a livable world. Even after the Moon formed, the young planet kept gathering material from the disk around it, though more slowly now as the surrounding debris grew thinner. Some of that late arriving material is thought to have delivered elements the Earth's earlier, differentiated layers had already lost, including certain metals that should, by rights, have sunk entirely into the core, but instead remain, in small amounts, in the mantle and crust today. Geologists sometimes call this later dusting of material the late veneer, a final layer added after the planet's basic structure had already been set. Picture, if you can, what that Earth might have looked like. A dim, glowing landscape of molten or half-molten rock, lit from within by its own heat rather than by any calm daylight. Its thin, forming atmosphere made of gases no living thing could have breathed, its surface still shuddering. Every so often, under the impact of debris left over from the solar system's birth, there was no blue sky yet, no sound of wind or water, just heat and rock, and the slow turning of a very young world, its glowing surface gradually, unevenly, beginning to darken and stiffen at the edges, the way molten metal skins over as it cools. Geologists call this earliest chapter of Earth's story the Hadean, after Hades, the underworld of Greek myth. A fitting name for a planet that, for a long while, looked very little like a home. Slowly, though, that would begin to change. As the young Earth continued to cool, another transformation was already beginning. As the young Earth cooled, its glowing surface slowly began to change character. The outermost layer, exposed to the deep cold of space, started to harden into a thin crust. Though this early crust didn't last long in any one form. Volcanic activity kept breaking it apart, melting it and reforming it again and again as the planet continued to seethe underneath. If any early crust survived for long, it would likely have looked less like the stable continents we know today, and more like the crust of a lava lake, dark, cracked plates drifting on molten rock, sinking and reforming in an endless, restless cycle. We have almost nothing left from this period. Few rocks that old have survived the Earth's long and restless history. What has survived are tiny, remarkably tough crystals called zircons, discovered in a low range of hills in Western Australia known as the Jack Hills. Zircon crystals are almost indestructible by geological standards, able to survive being melted, buried, uplifted and eroded over and over while still preserving, locked inside their structure, a faithful record of the conditions under which they first formed. Some of these Jack Hills zircons have been dated to roughly 4.4 billion years ago, barely 100 million years after the Earth itself began to form. And these tiny crystals have hinted at something surprising. Liquid water may have existed on Earth's surface far earlier than scientists once assumed, perhaps even during this earliest, harshest stretch of the planet's youth. The evidence lies in the particular way certain elements are distributed within the crystals, patterns that, on Earth today, only seem to form in the presence of water. It's a debated idea, based on subtle chemical clues rather than direct proof, but it has gained more support in recent years, and it raises the intriguing possibility that oceans of some kind may have appeared on Earth almost as soon as there was a solid enough surface to hold them. Where did all that water come from in the first place? Nobody knows for certain, but two explanations are generally favored, and they may both be partly true. Some of the water might have been locked inside the very rock and dust that built the Earth, released slowly to the surface as volcanic gas once the planet began cooling and separating into layers. And some of it may have arrived later, carried in by collisions with icy asteroids and comets from farther out in the solar system, where conditions were cold enough for ice to survive. By comparing the chemical fingerprint of water in Earth's oceans with water found in various asteroids and comets, scientists have found that asteroids were probably the bigger contributor of the two, though the exact balance is still being worked out. And every new comet or asteroid sample returned by a spacecraft tends to shift the picture slightly. However it arrived, by some point within the first few 100 million years of Earth's existence, enough water had gathered and enough of the crust had cooled for the very first oceans to form. These were not oceans as we'd recognize them. Picture a world of dark volcanic islands rising out of steaming, restless seas under a sky that would have looked strange to modern eyes. Thick, hazy, and lit by a sun that was itself somewhat dimmer than it is today. Perhaps 20 or 30% fainter, a puzzle astronomers call the faint young sun paradox. Since a fainter sun should, by simple arithmetic, have left the early Earth frozen solid, and yet the geological evidence says otherwise. The likely answer lies in the atmosphere itself, a thicker blanket of greenhouse gases holding in far more heat than our modern air does, keeping the oceans liquid despite the dimmer light falling on them from above. That atmosphere overhead had almost nothing in common with the air we breathe now. It was made mostly of carbon dioxide, nitrogen, and water vapor, released from volcanoes across the planet's surface, and it held essentially no oxygen at all. That absence of oxygen matters a great deal to what comes next, because it was inside this oxygen-free world that life itself first appeared. Around 4 billion years ago, the inner solar system seems to have gone through a stretch of especially heavy bombardment, a period sometimes called the Late Heavy Bombardment, during which the Earth, the Moon, and the other rocky planets were struck by asteroids and leftover debris more often than usual. One proposed explanation involves a slow, gradual shifting in the orbits of the giant planets farther out in the solar system, particularly Jupiter and Saturn. As their orbits settled into a new configuration over millions of years, the theory goes, their combined gravity would have stirred up a distant belt of small, icy bodies, scattering a portion of them inward toward the Sun and toward the Earth. This isn't a settled fact. Some scientists still debate whether it was truly a distinct, intense event or simply the tail end of the solar system's general early chaos, gradually winding down. Much of the evidence comes from the Moon, whose ancient, undisturbed craters preserve a record, the restless Earth erased from its own surface long ago. Whatever the details, it's fair to say the young Earth spent a long stretch of its childhood under fire, struck again and again by rocks falling out of the sky. Hardly a gentle place for anything alive to get started. And yet, something did get started. How life first appeared on Earth remains one of the great open questions in science. no one has yet worked out the full picture, and it's worth being honest about that from the outset. What scientists can describe with reasonable confidence are the general conditions that seem to have been necessary, and a handful of promising ideas about how the first steps might have happened. At its most basic, life needs three things: a way to store and pass on information, a way to carry out the chemical reactions needed to stay alive, and some kind of boundary separating itself from the outside world. In every living thing today, these jobs are handled by three different kinds of molecule: DNA for storing information, proteins for doing most of the chemical work, and fatty membranes for holding a cell together. One widely discussed idea, known as the RNA world hypothesis, suggests that earlier, simpler life might have relied on just one molecule to do two of these jobs at once. RNA, a close cousin of DNA, can both store genetic information and, in some forms, help drive chemical reactions, which would have made it a natural starting point before life split those tasks between separate molecules. Where might this first chemistry have taken place? Two settings come up again and again in the research. One is the ocean floor itself at hydrothermal vents, places where seawater seeps down into cracks in the Earth's crust, gets heated by volcanic activity below, and rises back up again, carrying dissolved minerals with it. A particular kind, called alkaline hydrothermal vents, forms delicate, porous mineral structures, sometimes rising many meters off the seafloor like pale mineral chimneys that create natural chemical and electrical gradients, not unlike the ones living cells use today to generate energy. It's easy to imagine such a vent, a slow plume of warm, mineral-rich water rising through darkness on the seafloor, far from any sunlight, chemistry quietly unfolding in the dark, undisturbed by storms or tides or the harsh, unfiltered light still striking the surface far above. The other setting proposed is much closer to the surface. Shallow pools of water, warmed and occasionally dried out by sunlight, then refilled again, gathering along the edges of volcanic islands or quiet lagoons. Charles Darwin himself, in a private letter written in the 19th century, once speculated about life beginning in what he called a warm little pond. And while the science has moved on a great deal since then, the basic image has proven remarkably durable. These repeating cycles of wetting and drying might have helped simple molecules link together into longer, more complex ones, the kind of chemistry that's difficult to achieve underwater but easier at a sunlit, evaporating shoreline. Neither idea rules out the other. Life may even have had more than one false start in more than one kind of place before something finally took hold and endured. Some researchers have also pointed to the steady rain of material falling from space itself. Meteorites recovered on Earth today are sometimes found to contain simple organic molecules, including some of the same basic chemical building blocks used by living cells, suggesting that at least part of the raw material for life may have arrived from beyond the planet altogether, seeded gently into Earth's early oceans by the same asteroids and comets that had, not long before, been raining down as part of the late heavy bombardment. However it began, all life alive today, from the simplest bacteria to the largest whale, appears to share a single common ancestor, a single ancient population of cells, sometimes referred to by scientists simply as Euka, the last universal common ancestor. This doesn't mean Luca was the first living thing, only the earliest one whose descendants are still traceable in the DNA of everything alive now. Whatever came before Luca, in that uncertain window before life stabilized into something recognizably alive, remains hidden from us, lost to time. The oldest solid evidence we have for life comes from structures called stromatolites, layered mounds built up as ancient microbial communities trapped and bound together fine sediment, one thin layer at a time. Similar structures can still be found today, growing slowly along a handful of remote salty coastlines, offering the rare living glimpse of a process that has otherwise been running quietly for billions of years. Some fossil stromatolites found in ancient rock in Western Australia date back roughly 3.5 billion years. Other tentative traces of life have been reported from even older rocks in Greenland, among the oldest surviving rocks on Earth. A few researchers have pointed to still older, more subtle chemical traces in rocks as ancient as 4.1 billion years, though those claims remain hotly debated since it's difficult to tell biological signals apart from ordinary chemistry in rock that old and that worn down by time. What we can say with some confidence is this: life, in some very simple form, had established itself on Earth by around 3.5 billion years ago, and quite possibly earlier still, arriving remarkably early in the planet's history, in an environment that would have seemed, by almost any modern standard, close to unlivable. For a very long time afterward, that life would remain small, simple, and largely unnoticed by the planet around it. But slowly, it was about to start changing everything. For a very long stretch of Earth's history, life stayed simple. Single-celled, invisible to the eye, quietly drifting through ancient seas. These early organisms, known as prokaryotes, had no nucleus and none of the internal structure found in more complex cells. Many of them made their living from the raw chemistry around them, drawing energy from volcanic compounds dissolved in the water rather than from sunlight. That was about to change, and when it did, it would change the entire planet along with it. Somewhere in this stretch of deep time, a new kind of chemistry appeared: photosynthesis. In its most familiar form, photosynthesis is a way of capturing sunlight and using that energy to turn carbon dioxide and water into food, releasing oxygen as a kind of waste product. But the earliest photosynthesis probably didn't work quite this way. Early versions likely used other chemicals instead of water. Dissolved iron, perhaps, or hydrogen sulfide, the compound that gives certain hot springs their faint smell of rotten eggs, and released different byproducts, no oxygen involved at all. It was a later group of organisms, the cyanobacteria, that developed the oxygen-releasing version of photosynthesis we associate with plants today, built around a green pigment called chlorophyll, tuned to capture the particular wavelengths of light the sun sends down most abundantly. It was this small, unremarkable-looking group of microbes that would go on to reshape the Earth's atmosphere completely. Nobody knows the exact date this happened. Some evidence points to oxygen, releasing photosynthesis appearing as early as 3 billion years ago, possibly earlier. But here's the strange part. For a very long time after cyanobacteria began producing oxygen, that oxygen didn't build up in the atmosphere at all. The ancient oceans were full of dissolved iron, and that iron soaked up the new oxygen almost as fast as it was made, reacting with it and settling out as solid rust layer by layer onto the sea floor. You can still see the result of that slow, patient chemistry today in striking rock formations called banded iron formations, alternating red and grey stripes of iron, rich and iron-poor rock, each band a record of oxygen being produced and then consumed over and over for millions of years. Enormous deposits of these formations survive today in places like the Hamersley Range in Western Australia and around Lake Superior in North America. Layered cliffs of red and silver rock, entire mountainsides built, quite literally, from ancient rust. These formations are mined for iron ore today. In a very real sense, some of the steel in the world around you was once dissolved in an ancient, oxygen-starved sea. Eventually, though, the ocean's iron ran low. There was nothing left to soak up the oxygen cyanobacteria kept producing, and for the first time, oxygen began building up in the atmosphere itself. This turning point, around 2.4 billion years ago, is known as the Great Oxidation Event, and it stands as one of the most dramatic transformations the planet has ever gone through. For the countless microorganisms that had spent over 1 billion years evolving in a world without oxygen, this new gas wasn't a gift. It was closer to a poison. Oxygen is a highly reactive element, and for organisms adapted to living without it, its sudden arrival may have been catastrophic. Some researchers consider the Great Oxidation Event to be among the earliest mass extinctions in Earth's history, though the fossil record from this period is thin, and much of that story remains hidden from us. The rise of oxygen had another, less obvious consequence, one that struck at the planet's climate directly. Before this point, methane, a powerful greenhouse gas produced by certain microbes, had likely been helping to keep the young Earth warm, working alongside carbon dioxide to compensate for that fainter, younger sun mentioned earlier. Oxygen reacts readily with methane, breaking it down, and as atmospheric oxygen rose, it's thought to have stripped much of that methane blanket away in a relatively short span of geological time. With one greenhouse gas suddenly weakened and the sun still not at full strength, the planet appears to have plunged into its very first widespread ice age. A series of glaciations called the Huronian, stretching from roughly 2.4 billion years ago to about 2 billion years ago. In a strange sort of way, the very organisms that had begun filling the air with the oxygen future life would depend on may also have frozen the planet nearly solid in the process. But where one kind of life struggled, another kind found opportunity. Oxygen, dangerous as it was, also made possible a far more efficient way of generating energy from food, one that would eventually allow for larger, more complex forms of life than anything that had come before. It's around this same time that scientists believe a truly pivotal event took place inside individual cells, the origin of the complex cell, the kind with a nucleus and other internal structures, the kind found in every plant, animal, and fungus alive today, including us. The leading explanation, called the endosymbiotic theory, is a strange and wonderful idea. It suggests that mitochondria, the tiny structures inside our cells that produce most of our energy, were once free-living bacteria in their own right. Instead of being destroyed or digested, it stayed. Over time, the two became inseparable, one living permanently inside the other to everyone's benefit. A similar story, playing out somewhat later, explains where plants and algae got their own remarkable ability to photosynthesize. Chloroplasts, the green structures inside plant cells that actually carry out photosynthesis, appear to be the descendants of cyanobacteria themselves, swallowed in much the same way, taken in by a different host cell, and never let go. In a sense, every green leaf on Earth today is still quietly running the same ancient chemistry. Those early cyanobacteria first developed billions of years earlier, now working from inside the cells of an entirely different organism. This idea sounded far-fetched when first proposed in the 1960s, but the evidence has held up remarkably well. Mitochondria and chloroplasts alike still carry their own small stretch of DNA today, distinct from the DNA in the cell's nucleus and much more closely related to bacteria than to us. This whole span of Earth's history, from roughly 2.5 billion years ago to about 540 million years ago, is called the Proterozoic, a name that simply means earlier life. It covers the Great Oxidation Event, the rise of complex cells, and, later on, one of the strangest and most extreme chapters the planet has ever lived through. For a very long stretch within this eon, roughly from 1.8 billion years ago to about 800 million years ago, the planet seems to have settled into a period of remarkable evolutionary calm. Some scientists have nicknamed this stretch the Boring Billion, only half joking. Continents drifted, oceans persisted, single-celled life carried on much as it had for ages. But the fossil record shows relatively little dramatic change compared to what came before and to what would come after. Deep ocean waters during this time are thought to have remained largely without oxygen, and often rich in dissolved sulfur, a condition scientists call euxinic, tinting the deep sea a hostile, sulfurous environment even as oxygen slowly accumulated nearer the surface above. It would be a mistake to think nothing important happened during this long, quiet stretch. Complex cells were still slowly diversifying, and the machinery of multicellular life was likely being assembled piece by piece out of view. But compared to the drama on either side of it, the Boring Billion earns its name. That long calm would not last. Somewhere between about 717 million years ago and 635 million years ago, the Earth seems to have frozen over almost entirely, not once but several times, in a sequence of extreme ice ages known today as the Cryogenian period, and often described using the evocative term Snowball Earth. Two of these glaciations, named the Sturtian and the Marinoan after the regions where evidence for them was first studied, appear to have been especially severe. Some researchers connect their onset to the breakup of the supercontinent, Rodinia, around this time. As that ancient landmass split apart, more coastline and exposed rock than usual would have been available for weathering, a process that naturally draws carbon dioxide out of the atmosphere, potentially cooling the planet enough to tip it into runaway glaciation. While there's still debate over exactly how complete the freezing was, whether the entire ocean truly froze solid from pole to pole, or whether a band of slushy open water may have persisted near the equator, the evidence for extensive glaciation, glaciers reaching all the way down to the tropics, is hard to argue with. Try to picture that world. Ice stretching to every horizon. frozen oceans, locked beneath a crust of white and grey, silent under a dim, hazy sky. Any exposed rock would have looked dark and stark against endless fields of snow and ice. An entire planet gone quiet and still. It's a striking image. Earth, the world that would one day hold rainforests and coral reefs, wrapped instead in an ice age so severe it makes the recent ice ages look mild by comparison. How does a planet get itself into that state? And more importantly, how does it get back out? The mechanism is something scientists call the ice albedo feedback. Ice is highly reflective. Pure white ice bounces sunlight back into space rather than absorbing it. So once ice starts to spread, the planet reflects away more sunlight, which cools it further, which allows even more ice to form. It's a loop that feeds on itself, and once it gets going, it's hard to stop. Getting out of a snowball Earth took something equally dramatic: volcanoes. With almost the entire planet sealed under ice, the usual process that removes carbon dioxide from the air. Rock weathering, which normally happens efficiently on exposed land. Ground almost to a halt. Volcanoes kept erupting anyway, pumping carbon dioxide into the atmosphere with nowhere for it to go. Slowly, that carbon dioxide built up, thickening into a powerful greenhouse blanket, until eventually it grew strong enough to overwhelm the ice albedo feedback entirely. The melting, once it began, would have been fast and violent by geological standards. An abrupt swing from a frozen world to an extremely hot one in what was, for the Earth, a fairly short span of time. Thick layers of a distinctive rock called cap carbonate, found today resting directly on top of ancient glacial deposits around the world, appear to record this sudden, dramatic thaw, laid down rapidly as the newly warmed oceans reacted with all that stored volcanic carbon dioxide. Remarkably, life came through these frozen ages more or less intact. Some researchers even suspect that the harsh conditions of snowball Earth and the wild swings in climate that followed each thaw may have helped push evolution toward greater complexity, perhaps by isolating small surviving populations from one another in scattered patches of open water, each left to evolve along its own path. Shortly after the last of these deep freezes ended, around 635 million years ago, the fossil record begins to show something new. The first simple, soft-bodied, multicellular animals, part of a strange and short-lived group known as the Ediacaran biota. They don't look much like anything alive today. Some, like the flattened, ribbed organism known as Dickinsonia, resembled little more than a quilted oval pressed into ancient mud with no visible mouth, limbs, or head. Others show faint traces of an early, three-part body structure, hinting perhaps at the first stirrings of the greater complexity to come. No shells, no legs, no obvious heads or tails, just soft, quiet, mysterious shapes drifting or resting on the seafloor, the earliest known animals to have left any trace of themselves behind at all. It was a modest beginning, but it was the beginning of something enormous. It's worth noting that oxygen levels themselves had not simply risen once during the Great Oxidation Event, and then stayed put for the following 2 billion years. For much of the boring billion, atmospheric and oceanic oxygen appear to have leveled off at levels still considerably lower than today's, enough to support simple, small-bodied life, but likely too low to fuel anything larger or more active. It was only later, in the centuries and millennia surrounding the snowball Earth episodes just described, that oxygen appears to have climbed a second time, in a rise sometimes called the Neoproterozoic oxygenation event, edging the atmosphere closer to something resembling its present composition. Many researchers see this second rise as closely connected to the appearance of the ediacaran organisms. Larger, more active animals generally need more oxygen to fuel their bodies than simple microbes do. And it may be no coincidence that the first substantial animals appear in the fossil record not long after the air and water around them finally had enough oxygen to support them. A burst of animal diversity and complexity unlike anything the planet had seen before was coming, and it's to that burst that we turn next. Around 540 million years ago, something remarkable happened to life on Earth, and it happened surprisingly fast, at least by geological standards. Within a window of perhaps 13 to 25 million years, the fossil record shifts from a world of simple, mostly soft-bodied creatures to one bursting with new and often strange forms of animal life. This burst is known as the Cambrian explosion, and it's one of the most striking transitions in the entire history of life. Picture an ancient sea floor from this period. Shallow, sunlit waters, alive in a way the planet had never seen before. Early arthropods with jointed legs scuttling across the sediment, soft-bodied creatures drifting overhead, strange armored animals unlike anything alive today creeping along the bottom. Fossil beds from this period, such as the famous Burgess Shale in what is now Western Canada, preserve an almost dreamlike menagerie of creatures. Five-eyed animals on stalks, creatures bristling with rows of spines, others so unlike any living group that scientists have puzzled for over a century about where, exactly, they belong on the tree of life. Many of these early body plans would go on to become the ancestors of nearly every major animal group we recognize now. The arthropods, whose descendants include today's insects and crabs, the mollusks, ancestors of clams and octopuses, and the early chordates, an unassuming little group that would, in time, give rise to fish, amphibians, reptiles, birds, mammals, and eventually, us. No one is entirely sure why this happened when it did, or quite so quickly. Rising oxygen levels in the oceans probably played a role, giving animals the energy budget needed to grow larger and more active. The evolution of new genetic tools for building complex bodies likely mattered too. The same small set of master genes scientists have discovered controls body plan development across an enormous range of animals today, suggesting that once evolution stumbled onto this genetic toolkit, it could be reused and rearranged in countless new ways. And once the first predators appeared, an evolutionary arms race would have kicked in almost immediately. Prey species evolving shells, spines, and armor, predators evolving better ways to get past them, each side pushing the other toward greater complexity. Before following life any further, it's worth pausing to understand something happening beneath all of this, slowly and continuously, for the entire span of Earth's history, the movement of the continents themselves. The outer shell of the Earth, called the lithosphere, isn't one solid piece. It's broken into a number of large plates, drifting very slowly across the top of the mantle below, carried along by heat rising and sinking deep within the planet. Where two plates pull apart, molten rock rises up to fill the gap, cooling into new ocean floor. Where two plates crash into each other, one is usually forced downward, back into the mantle, often triggering volcanoes and earthquakes along the way. And where plates slide past one another sideways, the friction builds up and releases in fits and starts. The kind of movement responsible for earthquakes along faults like California's San Andreas today. Over hundreds of millions of years, this slow drifting has repeatedly gathered the continents together into single, enormous landmasses called supercontinents, only to tear them apart again. One such supercontinent, Rodinia, formed during the Proterozoic era discussed earlier. A later one, Pangaea, would come together much further along in Earth's story, and its eventual breakup, beginning around 200 million years ago, set the continents drifting toward the arrangement we recognize on a map today, an arrangement that, very slowly, continues to shift even now. Returning to the story of life, the tens of millions of years following the Cambrian explosion, sometimes grouped together as the Ordovician period, saw marine life continue to diversify at a remarkable pace in what researchers sometimes call the Great Ordovician Biodiversification Event. As though the Cambrian explosion had merely been the opening act, reef-building organisms spread across shallow seas. Early relatives of squid, their shells coiled or straight as spears, drifted through the water as some of the largest and most capable predators the oceans had yet produced. Simple corals began forming the first true reef structures, laying the groundwork, quite literally, for a style of ecosystem that would recur again and again throughout the rest of Earth's history. This flourishing came to an abrupt halt near the end of the Ordovician, around 445 million years ago, in what stands as the second largest mass extinction in Earth's history. The leading explanation points to a sudden, severe ice age, as glaciers spread rapidly across a southern supercontinent called Gondwana, sitting, at the time, over what is now the South Pole. Picture that ancient pole, not open ocean as it is today, but a vast, ice-bound landmass, its glaciers grinding slowly outward toward warmer latitudes, locking up enormous volumes of the world's water as ice and causing sea levels to plunge across the entire globe. Shallow seas, home to the great majority of marine life at the time, would have shrunk dramatically or vanished outright in many regions, taking a substantial share of the planet's species with them. Once again, though, as would happen so many times across the following hundreds of millions of years, life endured and slowly began to recover. The following period, the Silurian, saw two developments of particular importance. In the oceans, fish continued to diversify, some of them now protected by early jaws, a significant advance over the round, sucking mouths of earlier jawless fish, allowing for an entirely new range of feeding strategies. And on land, plants took their first confident steps beyond the water's edge. Among the earliest true land plants was a small leafless organism called Cooksonia, standing only a few centimeters tall, little more than simple branching stalks, yet representing an enormous evolutionary achievement. A plant capable of holding itself upright in air, transporting water internally rather than relying on direct contact with a wet surface. It's worth picturing what the land looked like before this happened: bare rock and soil, exposed to a sun and wind that nothing had ever really had to withstand before, utterly silent, with no rustle of leaves anywhere on the entire planet, because there were no leaves. And then, slowly, the first green fringes began to appear along the water's edge, low mats and simple stalks creeping outward across the once barren ground. Where plants went, animal life soon followed, because plants meant food and shelter and a foothold. Early arthropods, ancestors of today's insects, spiders, and their many relatives, were among the very first animals to make the move onto land, with fossil evidence for land-dwelling arthropods appearing by around 428 million years ago. They found a world with no predators yet, no competition, an entire continent's worth of opportunity waiting to be explored. Vertebrates followed a little later, and their journey onto land was more gradual, more hesitant. In shallow freshwater streams and swamps, a group of fish with strong, fleshy fins, more like stubby limbs than typical fish fins, slowly developed the skeletal strength to support their own weight out of water, and simple lungs or lung-like structures to breathe air rather than pull oxygen from water through gills. By around 375 million years ago, these transitional creatures had given rise to the first true tetrapods, four-limbed vertebrates, the ancestors of every amphibian, reptile, bird, and mammal that would ever walk the earth, humans included. This period, the Devonian, is sometimes called the Age of Fishes, and for good reason. The oceans and freshwater rivers of this time were home to an extraordinary range of armored fish called placoderms, some of them modest and unassuming, others, like the massive predator Dunkleosteus, growing to the length of a small bus, their heads sheathed in bony armor plates that worked against one another like a pair of self-sharpening blades rather than true teeth. It would have been an unsettling place to swim, a world of armored giants patrolling reefs and river mouths alike. On land, meanwhile, plants continued their steady advance, growing taller and more complex with each passing million years. By around 385 million years ago, the earliest true trees had appeared. Among them a genus called Archaeopteris, which, despite the name, was not a bird at all, but a tree with fern-like leaves and a woody trunk, forming some of the very first true forests the planet had ever seen. Tall, quiet groves rising over swampy ground, entirely unlike any forest alive today, yet unmistakably forests all the same. The Devonian ended, as the Ordovician had, in a period of severe extinction spread out across perhaps 20 million years rather than arriving as a single sharp event. The precise cause remains debated, though the spread of those very first forests may, strangely, have played a role. As roots dug deeper into the land for the first time, they would have accelerated the weathering of rock on a scale never seen before, drawing down atmospheric carbon dioxide and potentially cooling the planet, while also washing unprecedented quantities of nutrients into rivers and coastal seas, possibly triggering algal blooms that stripped the water of oxygen. It is a curious thought. The same plants that were making the land livable may have helped destabilize the seas. Life recovered, as it always seemed to, and the following period, the Carboniferous, brought a world unlike anything before or since. Vast, humid swamp forests spread across the low-lying continents, filled with towering, tree-sized ferns and club mosses, some reaching 30 meters or more into a warm, heavy, oxygen-rich air. Atmospheric oxygen levels during this period climbed to some of the highest ever recorded in Earth's history, quite possibly above 30%, compared to about 21% today. That extra oxygen, along with the way insect respiration works, appears to have allowed some arthropods to grow to an almost startling size. Dragonfly-like insects with wingspans approaching a meter, millipedes longer than a grown adult is tall, ambling through the leaf litter of these ancient swamps. Picture those forests, dim green light filtering down through an immense humid canopy, the air thick and warm, the ground soft with endless layers of fallen fronds, and everywhere the low hum and rustle of oversized insects moving through the undergrowth. Over millions of years, as these swamp forests died back and were buried layer upon layer under sediment without enough oxygen present to let them fully decay, their remains were slowly compressed and transformed into vast underground seams of coal. The very same coal that hundreds of millions of years later, humans would dig from the ground to power much of the modern industrial world. In a very real sense, the warm, dim light of those ancient carboniferous forests is still, indirectly, lighting rooms and turning machinery today. On land, amphibians thrived in these humid, swampy environments, but they remained tied to water for reproduction, their eggs vulnerable to drying out if laid too far from a pond or stream. It was the evolution of a new kind of egg, one with a protective shell and internal membranes capable of retaining moisture on dry land, sometimes called the amniotic egg, that finally freed vertebrate life from the water's edge for good. This innovation gave rise to the reptiles, a group that, once it appeared, was able to spread deep into drier, harsher parts of the continents that amphibians had never been able to reach. Among the early reptile lineages at this time were the first synapsids, a group that looked, to modern eyes, something like a cross between a lizard and a dog, and that would, tens of millions of years later, give rise to the mammals. Though that story still lay very far in the future. By this point in Earth's history, the drifting continents were slowly converging. Piece by piece, over tens of millions of years, nearly all of the planet's landmasses came together into one immense supercontinent, Pangaea, fully assembled by around 300 million years ago. Imagine standing at its center. Nothing but land stretching in every direction for thousands of kilometers. A vast, dry interior, far from any ocean's moderating influence, prone to extreme heat and extreme cold, and very little rain. Along Pangaea's coastlines, life would have looked lush and familiar in places, still fringed by swamp forests and shallow seas. Deep in its interior, conditions would have resembled some of the harshest deserts on Earth today, only on a nearly unimaginable scale. A red-brown expanse of dune and dry riverbed stretching for what would have felt, to any traveler, like forever. The period following the formation of Pangaea, the Permian, saw synapsids continue to diversify, becoming, for a time, the dominant large land animals on the planet. Some plant-eating, some carnivorous, ranging in size from small burrowers to creatures as large as a modern rhinoceros, with a few sporting tall, sail-like structures of skin and bone along their backs, likely used to regulate body temperature under Pangaea's fierce sun. For a while, it must have seemed as though these mammal-like reptiles had inherited the Earth. It was against this backdrop, a single, vast supercontinent, its interior baking under an unbroken sun, its synapsid rulers spread across every corner of it, that the most severe crisis in the entire history of life took place. Around 252 million years ago, at the boundary between the Permian and Triassic periods, something went badly wrong with the planet. Massive volcanic eruptions, centered in what is now Siberia, poured out an immense, sustained flood of lava and volcanic gas, not in one dramatic burst, but over what may have been hundreds of thousands of years. The lava alone, once it finally stopped flowing, would come to cover an area comparable to the whole of modern-day Europe. Carbon dioxide levels climbed sharply. The planet warmed, by some estimates, as much as 8 or 10 degrees on average. The oceans grew more acidic, and oxygen levels in the water dropped, suffocating vast stretches of marine life. On land and at sea together, somewhere between 80 and 90% of all species vanished. It is, by a wide margin, the worst extinction the Earth has ever experienced, so severe that scientists sometimes simply call it the Great Dying. Picture the aftermath, if you can bear to: shallow seas gone eerily quiet, coral reefs collapsed into rubble, forests reduced to standing dead wood across huge stretches of Pangaea's interior, rivers choked with sediment, washing down off a landscape stripped of any plant cover to hold the soil in place. Even the coal-forming swamp forests of the preceding period vanished almost entirely for millions of years afterward, leaving behind what geologists sometimes call a coal gap, a long stretch of the fossil record with almost no coal at all, a quiet, telling scar in the rock. It would have taken a very long time, millions of years, before anything resembling a healthy, thriving world returned. And yet, life did return. That is, in its own way, one of the most reassuring patterns in the entire story of the Earth. However severe the damage, life has always found a way back. The recovery took much of the early Triassic period to unfold, slowly at first, then gathering pace. Early Triassic ecosystems were, for a good while, strikingly simple compared to what came before. Dominated by a small number of hardy, adaptable species able to tolerate the harsh, unstable conditions of a still recovering world, before greater diversity and complexity gradually returned over the following 10 or 15 million years. Among the survivors and their descendants was a group of reptiles that would go on to define the next 150 million years of Earth's history: the dinosaurs. Their earliest ancestors were modest creatures, upright and fairly small, moving on two legs through a world still recovering from catastrophe. Alongside them, in the shadows, small, unassuming descendants of the surviving synapsids were also quietly persisting. The first true mammals, tiny, likely nocturnal creatures, appearing by the later part of the Triassic, though it would be a very long time before their descendants amounted to much. But as the Triassic gave way to the Jurassic, dinosaurs diversified rapidly, growing larger, more varied, and more dominant, spreading into nearly every terrestrial environment. Pangaea, and later its fragments, had to offer. Because by this time, Pangaea itself had begun to come apart. The same slow drifting of tectonic plates that had gathered the continents together tens of millions of years earlier was now pulling them apart again. Rift valleys opened, widened, and gradually filled with seawater, splitting the great supercontinent first into two large landmasses, often called Laurasia in the north and Gondwana in the south, and then, gradually, into the more familiar continents we'd recognize on a map today. This was an immensely slow process, unfolding over tens of millions of years, but its effects were profound. New coastlines, new shallow seas, new patterns of climate and rainfall, and new opportunities for life to diversify in isolation on increasingly separated landmasses. The Jurassic and Cretaceous periods, spanning roughly 200 to 66 million years ago, are the eras most people picture when they imagine the age of dinosaurs, and for good reason. This was a world utterly transformed from the dry, unbroken interior of Pangaea. Lush, warm, and humid in many regions, crisscrossed with inland seas, its landscapes ranged from towering conifer forests to vast fern-covered plains, over which some of the largest land animals ever to exist, enormous long-necked herbivores, some reaching lengths that would stretch across several city buses in a row, moved in search of food while smaller, swifter predators hunted in their shadow. The oceans, too, were transformed. While dinosaurs ruled the land, the seas belonged to a different set of reptiles entirely. Long-necked plesiosaurs paddling gracefully through open water on 4 broad flippers, and ichthyosaurs, dolphin-shaped hunters that, despite looking remarkably like modern dolphins, were not related to them at all, having evolved that same sleek, efficient shape independently, millions of years apart, simply because it happens to be an excellent shape for moving fast through water. Overhead, meanwhile, the skies had their own reptilian rulers. The pterosaurs, some no larger than a modern bird, others by the late Cretaceous growing to the size of a small aircraft, wingtip to wingtip, gliding on warm updrafts above the dinosaurs below. It was during this long span of time that flowering plants first appeared, sometime in the early Cretaceous, and their arrival changed the character of the planet's landscapes considerably. Before this, Earth's greenery had consisted almost entirely of conifers, ferns, and similar plants, with nothing resembling a true flower anywhere in sight, and the world would likely have looked, to modern eyes, oddly muted. Green, certainly, but without the scattered brightness of petals that we now take for granted in any summer meadow. Flowering plants spread quickly once they appeared in evolutionary terms, and their rise coincided with a rapid diversification of insects that fed on them and, in turn, pollinated them. Bees and butterflies and countless other species locked in a long partnership with flowers that continues to shape both groups today. It's worth pausing on that quietly remarkable fact, the color and scent of a garden. Something so ordinary now is a relatively late addition to the Earth's long story, arriving only in this final act of the age of dinosaurs. High above the dinosaurs, another transformation was quietly underway. Among the many branches of the dinosaur family tree, one lineage of small, feathered dinosaurs was gradually evolving the ability to glide, then to fly. Fossils from this period, particularly from certain fine-grained lake sediments in what is now China, preserve stunning detail of these feathered forms, some with wings remarkably similar in structure to those of birds alive today. Over time, this lineage gave rise to the birds, meaning that, in a very real sense, dinosaurs never entirely disappeared from the Earth. Their descendants are still here today in every bird overhead. Mammals, meanwhile, have been quietly present since not long after the dinosaurs themselves first appeared, though for the entire span of the dinosaur age they remained small, unassuming creatures. Many no larger than a mouse or a shrew, most likely nocturnal. living in the shadows and margins of a world the dinosaurs otherwise dominated. A handful of Mesozoic mammal fossils hint at slightly more adventurous lifestyles. One remarkable specimen appears to have died with the remains of a small dinosaur in its stomach, a reminder that even in a world of giants, small creatures were finding their own ways to get by. Still, there was little reason, looking at the Earth during the Cretaceous, to expect that this modest, easily overlooked group would one day inherit so much of the planet. Then, around 66 million years ago, everything changed again, and this time, the cause is about as certain as anything in the fossil record can be. An asteroid, roughly 10 kilometers across, struck the Earth near what is now the Yucatan Peninsula in Mexico. Try to imagine the moment itself, a point of light brightening in the sky, faster and faster, and then an impact releasing more energy than can be easily put into words. Enough to gouge out a crater more than 100 kilometers wide, now known as the Chicxulub crater, and enough to trigger immediate devastation across the surrounding region, shockwaves flattening forests for hundreds of kilometers in every direction, wildfires racing across whole continents, and a wall of ocean water thrown outward as a colossal tsunami, taller than most buildings, surging far inland along every coastline within reach. But the immediate destruction, as vast as it was, wasn't the worst of it. The true damage unfolded over the months and years that followed. Dust, soot, and vaporized rock thrown high into the atmosphere spread around the entire globe, blotting out much of the sunlight for what may have been months or even years. Picture a world thrown into a long, artificial twilight. Plants, unable to photosynthesize properly, temperatures dropping sharply despite the recent warmth of the Cretaceous, food chains collapsing from the bottom up, on land and in the oceans alike, as the tiny drifting algae that support most marine life simply had no light left to grow by. The non-avian dinosaurs, after ruling the planet for over 150 million years, did not survive this. Their reign ended, geologically speaking, in the blink of an eye. Broadly speaking, the animals that made it through tended to share certain traits: small body size, the ability to shelter underground or underwater, and a diet that didn't depend on fresh living plant matter, since so much of it had, for a time, disappeared from the world entirely. Among the survivors was that single lineage of feathered, flying dinosaurs, the early birds, along with a great many other creatures small enough, adaptable enough, or fortunate enough to endure the dark years that followed. Also among those survivors were the mammals, still small and unassuming, but numerous and resilient, and, crucially, no longer living in a world dominated by dinosaurs. With that immense ecological space suddenly, catastrophically vacated, the stage was set for an entirely new chapter of Earth's story, one in which mammals, quietly overlooked for 150 million years, would finally have their turn. The period following the asteroid impact, stretching from around 66 million years ago to the present day, is known as the Cenozoic, the age of mammals, in the popular imagination, though the truth, as always, is a little more layered than that name suggests. With the dinosaurs gone from every ecological role except the skies, mammals expanded quickly, in evolutionary terms, filling niche after niche across the span of just 10 million years or so. Early primates appeared during this window, along with the ancestors of rodents and of the hoofed mammals that would later give rise to horses, deer, and their many relatives. The early Cenozoic was, for much of its length, a warm world, considerably warmer than today's, with lush forests reaching much farther toward the poles than they do now. That warmth was punctuated by one especially striking event, around 56 million years ago, known to scientists as the Paleocene, Eocene, thermal maximum. Over what appears to have been a remarkably short span of geological time, vast quantities of carbon were released into the atmosphere and oceans, probably from a combination of volcanic activity and the sudden release of frozen methane deposits from the sea floor, and global temperatures spiked dramatically, by perhaps 5 or 8 degrees, remaining elevated for roughly 200,000 years before slowly subsiding. Coral reefs suffered, and life in the deep ocean, adapted to cold, stable conditions, was hit particularly hard. And yet, on land, this warm, carbon-rich world seems to have suited many early mammals rather well. And it was around this same turbulent stretch of time that several major mammal groups, including the ancestors of horses, first appear clearly in the fossil record, some of them, curiously, no larger than a small dog. It was also during the early Cenozoic that one particular group of mammals made an especially striking decision, evolutionarily speaking, to return to the sea. The ancestors of modern whales were, at this point, four-legged, hoofed land mammals, distant relatives of today's deer and cattle, living along the shores of ancient Asia. Over a remarkably short span of some 10 million years, as documented by an increasingly complete fossil record, their descendants gradually lost their hind legs, developed powerful tails for swimming, and moved their nostrils higher and higher on the skull, eventually becoming the blowhole familiar on whales today. It stands as one of the most dramatic and well-documented transformations in the entire fossil record. A land animal, walking on 4 legs along a muddy shoreline, gradually becoming one of the largest and most graceful swimmers the oceans have ever known. Over the tens of millions of years that followed, Earth's climate began a long, gradual cooling trend. Shifting continents rearranged ocean currents. The opening of a deep passage around Antarctica, as that continent drifted into isolation near the South Pole, is thought to have allowed a powerful, cold current to encircle it uninterrupted, helping to seal it beneath the ice sheet that still covers it today. Long-term changes in atmospheric carbon dioxide played their part as well. Slowly, the lush warmth of the early Cenozoic gave way to a cooler, more variable planet, and grasslands, a relatively new type of ecosystem, began spreading across the continents in place of some of the older forests, favoring animals built for speed and open plains over those adapted to dense, sheltering woodland. That cooling eventually led, around 2.5 million years ago, into the Pleistocene, an age defined by its repeating ice ages. Enormous ice sheets crept southward across much of the northern hemisphere again and again, burying entire landscapes under kilometers of ice, then retreating once more during warmer interludes, only to advance again later. We are, in fact, still technically living within one of these warmer interludes today. These glacial cycles weren't random. They follow a slow, predictable rhythm tied to subtle changes in Earth's orbit and tilt. The shape of its path around the Sun stretching and relaxing over time. The angle of its axis wobbling very slightly, over cycles lasting tens of thousands of years. These are called Milankovitch cycles, named for the Serbian scientist who worked out the mathematics behind them in the early 20th century. Small as these orbital shifts are, they're enough to nudge the balance of sunlight reaching different parts of the planet. And over thousands of years, that nudge is enough to grow or melt an ice sheet the size of a continent. Picture the world during one of the deeper glacial periods, ice sheets several kilometers thick, smothering much of present-day Canada and northern Europe. Sea levels far lower than today, as so much of the planet's water sat frozen on land, exposing land bridges between continents that are now separated by open ocean. Across the cold, open grasslands beyond the ice, enormous animals roamed in herds. Woolly mammoths, their long, shaggy coats trailing almost to the ground. Giant ground sloths, taller than a modern giraffe. Saber-toothed cats stalking herds of bison and horses across a landscape that would look, to modern eyes, almost like a dream. Equal parts familiar and utterly strange. It was against this backdrop of a cooling, cycling planet that our own story, the human story, slowly began to unfold. Even within this long ice age, the climate was never perfectly steady. One particularly striking wobble occurred quite recently, in geological terms, around 12,900 years ago, just as the world seemed to be warming out of the last glacial period for good. Over what may have been only a few decades, temperatures in many parts of the northern hemisphere plunged back toward full ice age conditions, in an episode scientists call the Younger Dryas, named for a small Arctic flower whose pollen reappears in lake sediments from this time as a marker of the sudden cold. The likely cause was a sudden disruption of ocean currents, possibly triggered by a vast pulse of fresh meltwater pouring off the retreating ice sheets and into the North Atlantic, temporarily interrupting the same warm currents that keep much of Europe mild today. After roughly 1,200 years, the cold snap ended, in some places within only a decade or two, and the long, slow warming trend resumed, eventually settling into the milder, more stable climate of the present. Primates themselves stretch back much further to small tree-dwelling mammals from early in the Cenozoic, gradually developing the forward-facing eyes, grasping hands, and large brains, relative to body size, that would characterize the whole group. But the specific branch leading to us split away from the branch leading to chimpanzees, our closest living relatives, somewhere between 6 and 8 million years ago in Africa. What followed wasn't a simple, straight line toward modern humans. It was a long, branching, often overlapping family tree, with several different species existing side by side at various points, only one of which would eventually remain. Early members of this lineage, grouped under the name Australopithecus, walked upright on 2 legs, freeing their hands for other uses, though their brains remained closer in size to those of modern chimpanzees than to our own. One especially famous fossil skeleton, found in Ethiopia and known to researchers by the name Lucy, offers a remarkably complete picture of what one of these early relatives looked like, short by modern standards, fully bipedal, at home both on the ground and, quite possibly, still comfortable climbing into the trees at night. Later, a group known as Homo habilis appears in the fossil record, alongside some of the earliest deliberately shaped stone tools yet discovered, simple flakes and choppers, crude by later standards, but a clear sign of a mind beginning to plan ahead, to see a rock not just as a rock, but as something that could become a tool. Homo erectus followed, taller, with a notably larger brain. And remarkable in another way too, it appears to have been the first of our ancestors to leave Africa altogether, spreading gradually across large parts of Asia, and surviving in some form for well over 1 million years, longer than any other human species has yet managed, our own included, at least so far. Our own species, Homo sapiens, appears to have emerged in Africa sometime between roughly 300,000 and 200,000 years ago. The exact details are still being refined as new fossils and new genetic evidence come to light. Whether we arose in one place or gradually across a wider stretch of the African continent is still an active question. What's clearer is what happened next, beginning in earnest somewhere between 70,000 and 100,000 years ago. Groups of Homo sapiens began migrating out of Africa, eventually settling across nearly every habitable landmass on Earth, moving along coastlines, across the exposed land bridges of the ice ages, and eventually by sea, reaching even the most remote Pacific islands. Along the way, they weren't alone. In parts of Europe and Western Asia, they encountered the Neanderthals, a separate human species that had already been living successfully in these colder regions for hundreds of thousands of years, with their own tools, their own burial practices, and, evidence increasingly suggests, their own forms of symbolic thought and even art. In parts of Eastern Asia, a more recently discovered group called the Denisovans, known mostly from a handful of fragmentary bones and teeth, but confirmed, remarkably, through the DNA still preserved inside them. These meetings weren't purely separate. Genetic evidence recovered from ancient bones shows that interbreeding took place. And many people alive today carry small traces of Neanderthal or Denisovan ancestry as a quiet legacy of those encounters, tens of thousands of years later. By around 40,000 years ago, the Neanderthals had largely vanished as a distinct population, for reasons still debated among researchers. Competition with incoming Homo sapiens, a changing and increasingly unstable climate, or simply the slow absorption of a small population into a much larger one, are among the leading explanations, and more than one may be true at once. For the first time in a very long while, a single human species remained. For most of our species' history, humans lived as small, mobile groups of hunters and gatherers, moving with the seasons, following game and gathering wild plants, leaving little behind beyond scattered tools and the occasional cave painting, some of astonishing skill, preserved in caves in places like southern France and northern Spain. Then, beginning around 12,000 years ago, as the last great ice age drew to a close and the climate settled into the milder, more stable conditions of the current epoch, sometimes called the Holocene, groups of humans in several separate parts of the world began, independently, to plant crops and keep animals deliberately, rather than simply gathering what they found. Agriculture allowed populations to grow and settle and eventually build the first towns and cities, setting in motion the long chain of events that would, thousands of years later, lead to writing, to recorded history, and to a species capable of looking back across 4.5 billion years and reconstructing, however imperfectly, the whole of the story told across this account. Set against the vast scale of everything that came before it, the whole of human history is almost impossibly brief. Writing itself is only about 5,000 years old. If you compressed the entire 4.5 billion year history of the Earth into a single day, 24 hours from midnight to midnight. Modern humans wouldn't appear until the last few seconds before the following midnight. All of recorded history, every civilization, every war, every book ever written would fit into less than the final half second of that day. And the story isn't finished. The Earth, right now, is still quietly changing in ways too slow for any one lifetime to notice. The same tectonic plates that built mountain ranges and split apart Pangaea are still drifting today, at roughly the speed a fingernail grows. East Africa is slowly splitting along a great rift valley, a young ocean in the geological sense, still only beginning to open. Scientists who model these movements far into the future have sketched out possible arrangements for a new supercontinent, sometimes called Pangaea Proxima, or by other names, depending on which model of future plate motion is used. Though so much time separates us from that future, tens or hundreds of millions of years, that any such map remains, at best, an educated guess, a sketch of a world none of us will ever see. Closer to home, in terms of time, the current Ice Age cycle is itself expected to continue for the foreseeable future, driven by those same slow Milankovitch rhythms that have governed the advance and retreat of glaciers for the past several million years. Though the timing and shape of future glacial periods remains an active subject of study, complicated considerably by the influence of the present, comparatively brief, human presence on the planet's atmosphere and climate. Further out still, the Earth's fate is tied to the life of the Sun itself. For roughly the next 5 billion years, the Sun should continue on much as it has, steadily fusing hydrogen into helium, slowly growing very slightly brighter as it goes, in the same gradual way it has brightened since that faint, dim youth described earlier in this account. That slow brightening will, in time, somewhere between 1 and 2 billion years from now, make Earth too hot for liquid water to survive on its surface, bringing an end to most life as we know it, long before the Sun itself undergoes any dramatic change. The oceans, which took so long to fill, and which have carried the story of this planet from its very first single-celled organisms all the way to the present day, would slowly boil away into space, leaving behind a hot, dry, and lifeless world. Eventually, around 5 billion years from now, the Sun will exhaust the hydrogen fuel at its core and swell into a red giant, large enough that its outer layers may reach all the way out to where the Earth now orbits, though whether the Earth itself is engulfed outright or merely scorched and left as a bare, blackened ember in a wider orbit remains a detail scientists are still working out. Either way, whatever remains of the Earth by then will bear no resemblance at all to the quiet, blue, water-covered world it is tonight. That is an unimaginably long time from now. Longer, in fact, than the entire span of history already told in this account. In that sense, despite everything that has already happened, the collision that made the moon, the slow filling of the oceans, the first fragile life in a world without oxygen, the transformation of the atmosphere, the frozen ages, the explosion of animal life, the drifting and colliding of continents, the rise and fall of the dinosaurs, and the recent brief arrival of a species able to look back and piece all of this together. The Earth is, in a strange sort of way, still fairly young, still early in its own story, with a future ahead of it longer than everything that has already passed. For now, though, none of that lies close at hand. Tonight, as on every night for 4.5 billion years, the Earth continues along its slow, steady orbit around the Sun. Its continents drift almost imperceptibly beneath everything living on them. Its oceans rise and fall with the pull of a moon formed in violence long ago and now hanging quietly overhead, a little farther away tonight than it was when this account began, if only by the width of a few more atoms. Mountains that once didn't exist are still, this very moment, rising and eroding far too slowly for any human eye to see. Somewhere, a volcano is quietly building new rock, exactly as it has since the beginning. Somewhere, a coastline is being reshaped by water that has been rising and falling since before there were shores to reshape at all. Somewhere, deep in the mantle, heat left over from a molten world that formed 4.5 billion years ago is still, patiently, working its way toward the surface, the last faint echo of the Earth's fiery beginning. The same planet that once had no oceans, no forests, no sky worth looking up at, now turns gently in the dark, carrying all of it forward. The ice ages and the coal forests, the dinosaurs and the whales, the first fragile cell and every living thing descended from it, carrying you forward with it, too, into tomorrow. Rest now. The Earth will still be turning when you wake.